In this video, I will show you an example of how you can work with an ideal gas process. I went over the theory, and now I'm going to show you how you can work with one process. So let's say that the process that I have here to go from state 1 to state 2 is an isothermal process. And as I mentioned in a different video, let's say that the volume of state 2 is 2 times the volume of state 1. And in the past, I have found the pressure of state 1. So since this is an isothermal process, looking at the theory, I know that the change in temperature is 0 during this process, which means the change in the thermal energy is 0. And I have also I also have here the work that the gas does on the surroundings. It can be found as nRT ln V final over V initial. Now here you're going to use the number of moles of the ideal gas, and we will use the temperature. Remember, it's an isothermal process, so the temperature of state 1 state 2 is the same. Okay, you only have one number, and the natural log of the final volume, the volume of state 2 over the initial volume. Okay, so let's go and work with this process on a new blackboard. So here I'm going from 1 to 2, and it's an isothermal process, so delta T is 0. Because the change in the temperature is 0, I know that the change in the thermal energy is N3 over 2 K delta T. If you plug in the 0 here for delta T, you get a 0. Now, this means, okay, remember from energy conservation, we have this. And since I found delta E thermal is 0, if I use a 0 here, this means that 0 equals W plus Q. I will come back to this. Now, as I said, so let's make a note. This is an isothermal process. Now I know, remember I have the expression there, nRT, the natural log, V final over V initial, and I have numbers, so this means I can use 3 moles, remember I gave you the numbers in a different video, times 8.31 times, let's see, I think it is 373 for the temperature. Let's see if I remember correctly. Yes, 373 for the temperature, and then times the natural log. Now, what I remember is that, I'm gonna make a note. I know that V2 is V1 times 2. I don't remember the numbers, the specific numbers, but I do remember that they are V2 is double of V1. So V final is V2. Okay, so that means V final over V initial is really V2 over V1. V2 is 2 times V1 over V1. V1 with V1 cancels. So here the fraction inside the natural log is simply 2. So this will be the natural log of 2. And here is how I can find the work that the gas does on the surroundings. And this will give us 6,400 joules. Now, I do want you to remember, this is the work that the gas does on the surroundings. If I want to use energy conservation, as I said before, I have to include a minus here. So the work that the surroundings do on the system, on the gas, is going to be minus 6,400 joules. Okay, so let's call, okay, I don't have to number my equation, since I found the work that the surroundings do on the system. I can now go back to energy conservation and say 0 equals minus 6,400 plus Q, and this means Q is 6,400 joules. Now, what does that tell me? The fact that Q is a positive number means that some thermal energy was transferred from the surroundings to the system. So, for example, there was some energy, 6,400 joules was went from the surroundings to the system in the form of thermal energy transfer, due to a temperature difference. Now, I have the work, I have Q, I have the volume for state 2, I have other quantities for state 2. This is how, okay, with in this example, I'm showing you how you can work with an ideal gas process. Okay, and this here from 1 to 2, this is a process. Specifically, this is an isothermal process. This is how you will need to work with any ideal gas process. The only thing that you will have to do, if it is an adiabatic, if it is isobaric, instead of doing exactly the steps that I did, you will need to be using, let's see, where's my theory? You will need to be using different parts of the theory. So I was dealing with an isothermal process. That's why I used this theory. If you're dealing with an isobaric process, you have to use this theory. At the same time, you don't forget to use energy conservation as well. So that's the only difference between a different process of an ideal gas.